Welcome to this channel. Today we are going to discuss about the liquid crystal display (LCD) in avionics. Liquid crystal display (LCD) technology holds a premier position in modern avionics display systems due to its versatility and efficiency. Unlike other display types, the LCD functions fundamentally as a light valve, capable of operating in reflective, emissive, or transflective modes. The core principle of the LCD is its ability to turn ambient or supplied light on and off, making it adaptable to various lighting conditions, from bright sunlight to nighttime operations. Basic construction: a light valve at its heart, the LCD consists of a specialized fluid, the liquid crystal, sandwiched between two clear glass plates. Both the front and rear glass plates are coated with thin, transparent metallic films, acting as electrodes to apply an electric field. The front plate has these metallic coatings applied in specific, segmented areas to define the display elements, like digits or characters. The rear glass is coated entirely with a transparent metallic film. This basic arrangement is what defines the light valve mechanism, controlling the passage of light. Rather than emitting it directly, the physical construction of the display is key to its light modulating capabilities. The role of polarization and liquid crystals polarizing films: a polarizing film is applied outside both the front and rear glass plates. This film transforms randomly polarized ambient light into plain polarized light, restricting the electric field of light waves to a single plane, like a microscopic window blind. Liquid crystal properties: liquid crystals possess the unique ability to rotate the polarization of light as it passes through. This rotation is a direct function of the electric field applied across the crystal material, modulating light passage by changing the electric field. The liquid crystal rotates the light's polarity. If this rotation aligns or misaligns with the rear polarizer, the light is either blocked, resulting in darkness, or allowed to pass, resulting in a bright area. The interplay between the polarized light and the electrically controllable liquid crystal is what creates the selective opacity necessary for display function. Achieving contrast: white on black versus black on white polarizer alignment and affects the visual appearance, contrast, of an LCD display is determined entirely by the relative orientation of the front and back polarizing films. If the two polarizing films are aligned to the same polarization, light passes through initially. When an electric field is applied, the liquid crystal rotates the light by 90 degrees, causing the light to be blocked by the rear film. This results in a black on white display, where the energized areas become opaque, dark. Inverted alignment for contrast: conversely, if the polarizing films are oriented 90 degrees to each other, the display appears dark by default. Applying the electric field causes the liquid crystal to rotate the light by 90 degrees, allowing it to pass through the rear polarizer. This configuration produces a white on black display, where the energized areas become bright. Furthermore, to prevent unwanted chemical reactions, degradation, within the liquid crystal material, the applied electric field must alternate, ensuring no continuous DC component is maintained. Operational modes: reflective, emissive, and transflective LCDs offer flexible illumination modes, making them highly versatile for the varying light levels encountered in aviation environments. Reflective mode: the rear panel is a mirrored surface. The display uses ambient light, reflecting it back to the viewer. This mode is exceptionally low power and provides excellent sunlight readability without the need for a strong backlight. Emissive mode: a light source, backlight, is placed behind the display. The LCD shutters modulate this internal light source to create the image. This mode is necessary for low light or night operations and requires more power. Transflective mode: this hybrid mode uses a partially transparent mirror at the rear. It allows reflection of ambient light during the day and transmits internal backlighting during the night. This is a common and highly effective arrangement for avionics displays. The efficiency advantage: power and pixel density. A major compelling advantage of LCD technology is its minimal power requirement compared to emissive displays like LEDs. There are 4 power draw: 0 for energy for state change. Virtually zero energy is required to maintain or change the state of the liquid crystal material, open or shut the light valve. 0.10-20 MW for LED segment power. A single bright light emitting diode LED segment consumes 10 to 20 milliwatts, making large arrays impractical due to heat dissipation. 0.20 W for LED array dissipation. A 1024 element LED array, if fully activated, could dissipate up to 20 watts, which is too concentrated for typical avionics front panels. 0.1024 for LCD segments in small area. 1024 LCD segments can occupy a small area with no power or heat dissipation concerns related to the crystal material itself. So, the low power draw of the liquid crystal allows for very high segment counts, essential for complex graphics, without the thermal management issues faced by high-power emissive technologies. Next, from segments to graphics. These are the pixel problem in basic segment. There are few pixels and minimal drivers. And low-resolution graphic, there are 100 of pixels, many drivers. For high-resolution graphic, million of pixels, impractical drivers in TFT solution, thin film transistors used for enabling the scalable pixels. Active matrix liquid crystal display AMLCD. In this, the active matrix liquid crystal display AMLCD solves the complex connectivity problem by integrating the driving electronics directly onto the glass substrate. Thin film transistors, TFT, very small TFTs are deposited on the glass and connected to each individual segment, pixel. These transistors act as switches and storage elements. XY multiplexing. Each pixel is sequentially addressed at the intersection of horizontal and vertical lines, e.g., a 1024 by 1024 matrix is addressed by 2048 lines. The transistor stores the activation signal until the next refresh cycle. Integrated circuits. By mounting integrated circuits directly onto the glass and utilizing electronic multiplexing, the massive number of interconnects, 2048 plus, is drastically reduced to only a handful of lines. Color, resolution, and manufacturing challenges. Generating color graphics are produced by dedicating 3 light shutters, one for each additive primary color, red, green, blue, to every single pixel. Each shutter has a microscopic color filter. For a standard 1024 by 768 resolution display, 786,432 pixels. This results in over 2.3 million individual LCD light shutters and transistors. This immense density pushes manufacturing tolerances. Cost-driven by yield. The primary challenge for AMLCDs is manufacturing yield, since a display is often considered non-viable if even one pixel fails. The probability of successfully manufacturing 2.3 million perfect components is very low. For example, a display with a 4:3 aspect ratio and 1024 horizontal pixels means the resolution is 1024 columns by 768 rows. 1024 divided by 4 times 3 is equal to 768. Thank you, and don't forget to follow and subscribe my channel to know more about it.